Thanks everyone for joining. Welcome all the students here for the Radio Astronomy Winter School. So in some way, this is a part of a series of talks, I should say, though it was not designed that way. So in my talk today, I'll be talking about broadly cosmology because that's my area of research. But of course, I'll be covering different aspects of cosmology, a part of which also ties up with our experiment, which I will not have time to go into. And then followed by this, I believe Mayuri Rao will be talking a little bit more about the 21 centimeter part of it, which will be covering some regions of the cosmic timeline. And on the more experimental landscape, on Saturday, B.S. Girish will give you a glimpse of the deployments, the setting up of experiments, and other related challenges. So I would say that these three are a series of talks, and this is just to set the stage and solidify the foundations on which we understand these things. Okay. I'll get started. This is about an hour or so lecture on advances in cosmology, but I really want this to be very interactive. So in between, if any of you have any questions, you can raise hands. I can see all of you. And then someone from your end will probably unmute you and can relay the questions to me. And it's better that if it's done during the presentation rather than holding off the questions all the way to the end. Okay. So with this, let's get started. So essentially, all of you might be familiar with the night skies. Most importantly, I hope all of you have at some point seen very clear night skies, something that we don't do often in Bangalore at least. And what you are seeing here is one of such night sky images that a colleague of ours from Hanle, Dorje Amchuk, took and also taught me how to do astrophotography. So this was done roughly at 4,800 meters above the sea level. And maybe, Prabhu, if you can unmute it, I would want to ask certain questions. Is that okay with you?
Yeah, it's unmuted.
Yeah, perfect. Yeah. So people who are there, what all can you see here? So for example, who can tell me what this band is, which is not very often visible from at least urban regions?
Very loudly.
Milky Way bar.
Yes, this is Milky Way. But then what you also see are a lot of these dots. Some of them or most of them are stars, but many are not. Okay, there are extragalactic objects as well. So when we go to a clear night sky, we see all of these structures. Of course, we see our own galaxy, which is Milky Way, but then also other galaxies. Also, you can see a meteor here. And this is all with naked eyes, really, right? But we can certainly do better than this. And people have. So you all have heard about Hubble Space Telescope or James Webb Space Telescope. And what it has done is just focused on a very small patch of the sky and probed deeper into how many structures we see in our universe. Okay. And what you see here is remarkable. So this was one of the first deep field images, which was taken by the JWST telescope. And enormous number of very different galaxies, all different kinds of objects you see in significant patch of the sky. It's less than a degree actually. Okay. So our universe is very full of these exotic objects. Okay. And our digression question again, you see some of these structures to be very warped, right? They are almost feels like they're stretched. You see many of them like this. Any guesses of why our galaxy is looking like this? Lensing, perfect. Yes. So it also shows you that galaxies are not the only thing in the universe, or rather just the luminous objects. There are things much beyond. Okay. So in my talk, I will mostly be focusing on those non-luminous things. And then eventually I will point to more luminous things like stars. Okay. So This is a mandatory slide for any talk on cosmology, and I will take a little bit of a time to explain this. So, of course, the current understanding of the universe, I should say, is fairly recent. It kind of became an experimental science only from the 60s onwards. Before that, I should say cosmology was highly speculative. And this has mostly been the trend across astronomy and beyond, where your data is the thing that really drives the field, right? So you have to design experiments, you have to get some data, and that's the only way you can rule in models. So based on all of these very different observations from very different experiments, looks like this is the best model that represents our universe. And by this, I also want to clarify this is not the only model. This is the widely accepted one. There are people who also work on those alternate models, but that is something I would not touch upon during my talk. Okay. So under this, what we call as lambda CDM, lambda stands for dark energy and CDM stands for cold dark matter, something I will cover later in my slides. This is the cosmic timeline. So we will start with the region of very high density, very high temperature, something called as Big Bang, right? And it's often a misnomer. It's not an explosion. It's just that entire space-time is confined into a single point. So you cannot say, for example, in the universe, Big Bang happened here or there. It happened everywhere at the same time because entire space-time was confined into a very high region of density and temperature. And we kind of do not understand that very well because our physics knowledge is kind of constraining us, right? Because at those very high densities and high temperatures, you also have a lot of quantum mechanical effects. And because of the strong gravity, you also have general relativity effects. And you may know we have not been able to combine them. So Big Bang, probably we do not understand very well. What we understand is from where this timeline starts, which is roughly 10 raised to minus 32 seconds. Why this specific number, you may ask, and that's our homework. Try reading about Planck's second. Okay, so what we understand after Big Bang is there was a time, a very minute fraction, when the universe expanded exponentially. Okay, and that is what we call as inflation. Now, inflation also is very unconstrained because it's very difficult to observe it directly. Okay. We do have some signatures that people are planning to observe, but even as of today, we do not have a direct evidence that inflation occurred. But that is something indirectly explaining a lot of observations, so we kind of still believe it happened. Now, after inflation, you had universe as a very hot plasma. Okay, we are talking about temperatures of around 1000 billion Kelvin. And at that high temperature, you cannot have matter being neutral or forming atoms, right? So initially, and we are talking about microseconds to a few minutes, you have all these particles that are formed and they interact. Okay, we're talking about neutrons, protons, electrons. In your particle physics, you've also studied the whole standard model, pions, muons, and whatnot. All of them were formed around this time, a few seconds, and they were very strongly interacting with each other. I see. Now, at some point, you have the nuclei also forming in the first 3 minutes or so. But they are not completely independent. They are strongly coupled in this very hot plasma. But as the universe expands, it also cools down. This is adiabatic cooling. Okay. So what we are targeting now is to be able to form atoms. And the reason for that is only once the atoms are formed, you can actually form stars and galaxies. You need hydrogen. And only when you form stars and galaxies, we can exist. So it's like what we call as entropic principle. Because we exist, we know at some point atoms formed. And therefore, we know at some point atoms may have had independent existence and not in a coupled environment. So this decoupling happened around 400,000 years after Big Bang. And the reason is very simple. If electrons and protons tried to combine before that, what would happen is you have a lot of energetic photons. Okay, it's basically a thermal bath. And these energetic photons can come and knock off the electron and ionize the atom again, right? And this is like an equilibrium process. It keeps on happening. It keeps on happening till the point that photons are no longer energetic to ionize the atoms, right? Because photons are also losing their energy in the process. That happens around 400,000 years. And this is when you have the first atoms in the universe forming without being ionized again. So this is a very critical epoch, what we call as epoch of recombination. It's a misnomer again because re never happens. It's just combination. It's the first time that electrons and protons combine. But anyway, the naming is epoch of recombination. What also happens here, because photons have stopped interacting with the matter, photons can free stream. Okay. And these photons are visible to us even now. So the light which was emitted at the decoupling is exactly what we call as cosmic microwave background. Something I will very briefly cover. Okay. Another thing that you can do here, and that has a direct connection to RRI, is when this recombination happens, a lot of photons are emitted, right? So you have studied about hydrogen atom and different energy levels of hydrogen atom. So when the electron is captured and it trickles down to the lower energy states, it also emits photons. Those photons can in principle be detected even now. And there is an experiment going at RRI called Apsara, and you probably hear a little bit about it in the subsequent lectures, which is trying to look for that particular recombination radiation which was emitted when the first atoms had formed, okay, which has again not been detected yet by anyone. So that is about the first slide, which is the first atoms forming, after which for a very long period of time, nothing really happened. So we are talking about a regime where you have hydrogen gas, which is extremely neutral, and then you have photons, the cosmic microwave background, which is free streaming. And they are not talking to each other that way. So that period is what we call as dark ages. Okay, simply because nothing eventful happens there. But this changes around a few 100 million years after the Big Bang. Okay. And just to put that in context, as we know, the age of the universe is roughly 14 billion years as we measure it today. So we are still talking about the first billion years after the Big Bang. Okay. So the first stars form. Now, the question to you to think about, and if anyone has ideas, please tell me, is why didn't these stars form just after the first atoms? Why did it have to take from 400,000 years all the way to around a few 100 million years for stars to form? All they needed was hydrogen, and hydrogen had already formed here. Any ideas from the students?
Because maybe the density of the universe was equally balanced, maybe that time, and they could change after some time.
Okay, that's a very good track. Anyone else? Okay, density is the right word here. Yeah, sorry, someone said something?
No, go ahead. Sorry.
Okay. Yeah, so the point is you do need hydrogen gas, the neutral gas, but you also need high density, right? Because for a star to form, you need a high density region that can then collapse under its weight and then heat it sufficiently that the fusion process triggers, the nuclear fusion that we call it. Now, that cannot happen in the early universe simply because the densities are not high enough. Okay, and we are not talking about the density of the universe. So there is a distinction. You have a density of universe, but on top of that, you have fluctuations in the density. And that is very important. If a universe had uniform density, absolutely uniform, you cannot form any structure. We would not have existed. But what happened is, in background of that uniform density, there were regions that were slightly higher dense and slightly under dense. Okay. So the slightly higher dense region would start accreting more and more matter, and they would become more and more dense. And the regions which were under dense would become more and more under dense. So this kind of a setup, when you have these perturbations, you have this gravitational collapse, because at some point you can no longer accrete matter, right? So at some point you collapse, and that's when the star formation is triggered. So the densities, the over densities specifically, had to grow for some time before it could reach a limit where it can collapse and form stars. And that's why this delay. So we are talking about a delay of a few 100 million years for that to happen. Okay. And this is again a very interesting topic, because the first stars and galaxies in general would be very different from what we see today. Something I will cover in the last part of my talk if I get time. Okay. Now, after this, once the stars and galaxies form, you have a period where you have large scale structure, something on the right? This is what we call as the cosmic web. You have galaxies seeded into this, right? And they kind of sit over a whole range of filaments and sometimes voids. So that kind of started happening after the stars and galaxies had formed. And then a very peculiar thing happened relatively recently when we talk about cosmological scales, which is roughly 10 billion years, right? So just 3 billion years from us. And that is dark energy. So at this point, we understand that majority of the universe is actually comprised of dark energy. And it accelerates the expansion of the universe. It kind of works against gravity and is repulsive in nature. So it took up the expansion of the universe. So till before 10 billion years or so, from the Big Bang, universe was expanding, but it was kind of deaccelerating. But then when the dark energy started dominating, it kind of accelerated the rate of expansion. Something again I'll cover a little later. And this is what results in the large scale structure that we see today and the entire web of galaxies and other objects that we see around. Okay. So in my talk today, I will cover 3 different aspects, which is what I think I had alluded to in my opening slide. The first thing is cosmic microwave background, which is when the first atoms formed and the photons were released, which is what we see as CMB. And that soon after, well, cosmologically speaking, you had the first stars and galaxies form. This period we would call cosmic dawn. And finally, in the very later stages of the evolution, you have dark energy taking over and basically accelerating the expansion of the universe. Okay. So over our talk today, we will try to cover these aspects and see what's going on there. Okay. Any questions till now?
Yeah, please do.
It took only 1 microsecond to in the formation of neutron and proton, but it took 4 lakh years in the formation of proton. How could it be possible? Why? How is it?
Why it took?
Let's say in the formation of a neutron, proton, and electron, it took only 1 microsecond, but in the formation of a single proton, it took 4 lakh years.
So after the electron proton got formed, why it took so much time to form the first photon? Is the question.
No, photons, well, we should distinguish between the first light and first photons, okay? I think that's the confusion. The photons were very much here. As a matter of fact, you know the process of annihilation when particles can actually annihilate and produce photons and vice versa, okay? That happened very much within microseconds. So we are talking about existence of matter as well as photons in very early universe also. The first light that I'm talking about is not the formation of first photons, but streaming of the first photons. So before this, photons and matters were very tightly coupled. Okay, so they were interacting and therefore there was a lot of energy exchange. When this happened, which is roughly 400,000 years, somehow the photon energies were not sufficient to enable that interaction. So photons kind of stopped talking to the matter and they started free streaming. And we can only see things that are free streaming and reaching us. So in some way, we see the first light here, but the first photons are much, much earlier. I hope that answers the question.
Are you happy with that or not happy?
I'm not.
Okay, he's not yet fully happy, but I think maybe
Yes, the photons studying the matter. So they were not in neutron, proton, and electron. There was not actually matter term. It's matter terms have been using after so many like one first nuclei was from then after I don't know. So you actually said that the photons were stuck into the matter before that. So there was only neutrons, photons, and electrons. So do you mean that a photon was stuck in between the neutrons, photons, and electrons?
I'm not stuck. Yeah. Sorry, Prabhu, go ahead.
yeah, no. I was about to repeat. You were.
No, I heard. Yeah. So when we say first particles here, I think we can assume photons also. And when I say they interact, they can interact in various ways. Okay. This is something you will probably cover later. For example, there is Thomson scattering, there is Compton scattering, there is Bremsstrahlung. So there are different ways in which a photon and matter in general, but here we are mostly talking about electrons and protons, they can interact with each other. So they were very strongly interacting here, but they kind of stopped interacting here. So the demarcation here is the cessation of any interaction between them, right?
Okay.
Yeah, we can go ahead.
Sir, I also
One more
have a-
question. One more question.
So how
Yes.
did the first imbalance in the density came initially? Imbalance
Perfect.
in density. How did
Perfect. Yes, that's very much of a research problem, which is how did over densities and under densities actually started? And the most widely accepted model is it started right at inflation. So essentially, under very high densities and temperatures, you have what is called as quantum fluctuations or vacuum fluctuations. Okay, something I cannot go into the details of, but the idea is that
stochastic inflation is like one of reason
Yeah.
it can explain also, right? There's that-
yes. So there are different models. Stochastic inflation is one of them, but for example, there is this long roll inflation, chaotic inflation, eternal inflation. But all of them have one commonality, which is they need to seed these perturbations right in the very beginning. Okay. And that happened within that 10 raised to minus 32 seconds. So because of these vacuum fluctuations, which is common across the inflationary models, you have these perturbations seeded. The exact process of that seeding is not very clear even now. But they have been observed, and I'll come to that. Okay, so we will move on. And yeah, I really love this interaction. So please keep asking questions as we go across these slides. So if I put all of that into perspective, and I love showing this figure because it kind of incorporates the human timescales with cosmic timescales. What I talked about, most of it happened January, February, okay? Which is if we had to compactify all the 14 billion years onto a calendar, right? We are here in the final few milliseconds. 2023 is listed here. But the Big Bang and the formation of first stars already happened till here. And by May, you had Milky Way with you, right? So in the cosmology, we are mostly talking about the first few months of the Big Bang. As a matter of fact, I realized it's February and we are already at the first stars. So I will be talking about that. Okay. So like one of the student here asked, we have several unanswered questions and I have tried to compile all of them into a set of questions I think is important for cosmology. Of course, we cannot answer all of them today. But the very first question is, how did inflation even occur, right? That's a very, very important question to ask because you had a Big Bang. But what exactly led to expansion of that at a very accelerated pace? Okay, we don't understand that. And then the second question was rightly asked by the audience, which were how these primordial density fluctuations seeded on the space-time, because that's what led to the density perturbations, which eventually led to formation of stars and galaxies. So something we really don't understand. And then thanks to our CMB, we also know that we have plenty of dark matter and dark energy. As a matter of fact, what we see as atoms is just 5% of the whole universe or even less. Okay. So what exactly is this primary constituent of universe and how do we study that? And then of course, there is a question when universe began, you had equal amounts, or at least we expect we had equal amounts of matter and antimatter. Right? And you know that whenever a particle and antiparticle interact, they annihilate each other. So ideally, we should not have anything left. But given that we have matter, we see all around us, at some point, this asymmetry happened where the matter took over and it was more than the antimatter. And something we don't know why this would happen. And then, of course, the question about the physics. So when we write down the dynamics of the universe, at least for the background universe, is the physics same? So when we look at small scales, for example, galaxy or a cluster of a galaxy versus the physics that we use for large scale structures like filaments and voids, is the Physics same, and I'll tell later why is that even a question. And of course, after which, when the first stars formed, how different were they compared to what we see around us today? And the very first thing is why, how did they even form? And I'll come to why even that is a question, because the current channel of star formation is very different from the early star formation. And then what was the sources of these radiations? Was it just stars and galaxies, or there were other uh, objects in the universe which could produce these radiation, right? And people have talked about primordial black holes and other things. So these are some of the broad questions that I could think of that the current cosmology is trying to answer. And of course, I will not cover a majority of it. So I will start with CMB and slowly go towards dark matter, dark energy, and finally the first stars. So that is pretty much what we'll be doing today. Okay. And this background cosmology, I should highlight. One of the most important contributors was James Peebles, who also recently received a Nobel Prize in Physics for all the foundation work that he had done to establish the cosmological model that we just talked about. Okay. So the first thing is cosmic microwave background, and I have already talked a little about what happened. So again, just a recap, this happened around 400,000 years ago, after years later after Big Bang. And this is when the first atoms could comfortably form without being ionized by the photons. And these photons basically free streamed and resulted in cosmic microwave background. Now, this was predicted for a while. But again, as I said before, experiments has exactly what driven the science here. So the first experiment here came in 1965. Okay. And surprisingly, these people were not even looking for this. So Penzias and Wilson, these were engineers trying to develop a communication system. And as you will probably see in your tutorial sessions, you have some kind of an antenna that observes the sky, and then you have an associated analog and digital electronics. And they did that. They observed, they noted some powers that they were getting. And of course, in astronomy, I think Professor Rajaram has kind of talked about the units, which are very messy. But we are not talking about Kelvin as a thermal temperature, but Kelvin as a unit of power. Okay. So they measured power from different contributors. And what they got was something like 18 to 19 Kelvin. Okay. And this Kelvin is not physical temperature. And what they actually measured was roughly 3 Kelvin or 3.5 Kelvin higher than this. Okay. And it was not very sure what really caused it, because the first time you discover an anomaly like this, you probably do not want to attribute it to a standard model of cosmology. You want to check your instrument. And that's exactly what they did. They went to their antennas and saw some pigeon droppings on the antenna. And they also actually can contribute to different powers. So they cleaned up the whole system, but they continued to measure this. So at this point, a question for, again, students here, if you were at their place and you noted something as of an excess power, how would you confirm that this is coming from the sky and not from your instrument?
By checking the instruments for all the errors that can occur.
Perfect, which is exactly what they did. You have contributions from antenna, waveguide, maser, everything, converter. What else can you do?
Take the data again and again.
Wonderful, wonderful. Yes. So you need to have long-term observations. And one good thing about the cosmic microwave background is that it's all sky, right? It's not that the first atoms formed just here, right? They formed everywhere. So when we see from here to here, they should be visible over all the regions. So if you're seeing an excess power, you might want to scan different regions of the sky and see if you're getting the same amount of excess power from everywhere. So most likely, if it is instrument related thing, it may change with time, or it may change when you point your antennas to different directions. And these are very good debugging tools that you will use when you do projects. And here what they saw, it was not changing. Okay. And that's what kind of led them to come back to the conclusion that it might be cosmological. But see how careful they were when they reported this in a publication. They said, a measurement of excess antenna temperature at a certain frequency. And that's it. They have not mentioned anywhere in most of the paper what that could be. Just in passing reference in the last paragraph, there's like, okay, there are people who say this might be cosmic microwave background, right? So they have been very objective in what they have reported here. And that's a lesson for all of us. Okay. But of course, this generated a lot of interest, and people very soon confirmed that this is indeed cosmic microwave background, which kind of established lambda CDM model. Okay. And of course, there are other things. So we talked about density perturbations. These density perturbations will also be reflected in the CMB measurements. So the CMB is 3 Kelvin. It's all over the sky. But on that 3 Kelvin sphere, if you can imagine, there will be fluctuations. It will not be uniformly 3 Kelvin in all directions. That is what we call as anisotropies. So the figure that you see on your left is one of the pioneering figures of cosmology, which is trying to measure not the 3 Kelvin, but the fluctuations around 3 Kelvin, right? These fluctuations can be a few micro Kelvin. So we are going to very high sensitivities to be able to see these. Okay. And of course, there is a lot of information captured in this anisotropy, but what it also confirms, what I mentioned earlier about the density perturbations. So it's not just the theory that universe was uniformly dense, but with fluctuations. These fluctuations have been observed because they were imprinted on the cosmic microwave background. Okay. And then people, after the CMB 3 Kelvin was measured, people started trying to measure anisotropies. And this again is a very nice illustration of advances made in the experiments. So COBE was launched in the early 90s. And look at the kind of anisotropy that it measured. There is something hotter, there is something colder, probably not enough statistical significance, right? But then WMAP succeeded COBE. And now we are beginning to see much clearer things, much clearer anisotropies. And it's a very challenging experiment to say the least. And finally, 2000s or so, Planck was launched, which happens to be the last satellite that was launched for cosmic microwave background studies. And it further refined what Planck saw. So you can see it almost like you had a Gaussian kernel and you smoothed it to get WMAP, but these are different experiments. So the picture that I showed you here is from Planck, and it has really established the current cosmological model and proven that yes, CMB is there. There is anisotropy embedded on that CMB that actually tells a lot about different parameters of our cosmological model. Okay. So there are two measurements I talked about. One is the mean intensity, which is 3 Kelvin, and that you can measure at different frequencies. And what you will realize when you do that is that it's almost spotless black body. So black body means it's a single temperature. That single temperature is 3 Kelvin, and therefore it follows a Planckian spectrum. What you see here is not a fit. The COBE data is the plus sign, and you have just taken one temperature and plotted a Planck spectrum. And this is the most accurate black body known to humankind. These error bars have been enlarged by 400 times to just show you the data points. They are as exact on the black body as they could be. So that shows that CMB does follow what we predict from lambda CDM. And then what you're looking at the right is what we call as the power spectrum. So here you are not looking at the mean temperature, but you take this slice and you see how correlated power is at different scales. So this is mostly the spatial correlation of the powers, which is what we call as the power spectrum. So the x-axis is the angular scale and the y-axis is the correlation at those scales. And again, I can't get into the details, but this is also a very powerful tool to understand our cosmological model. Okay, widely enabled by missions like WMAP and Planck. So what has CMB told us? It can be another talk. So I will just summarize it in one slide. It has told, this is the list of papers that have come out from Planck, for example. So first of all, it also tells you a little about the medium between the CMB and U, right? So there are galaxies in between. There is our own Milky Way, which also is of lot of use to the community. So it has, for example, diffuse component separation, different kinds of foregrounds that we experience when we do these measurements. Then, of course, CMB power spectra that we just saw, this one. It also then looks at cosmological parameters, something I'll come about. This is basically encapsulating the densities of matter, of radiation, dark energy, dark matter. All of that comes from the CMB anisotropy measurements. Gravitational lensing, what we talked about, is also because CMB also gets lensed when it travels from the first 400,000 year slice to today. And that you can use to understand the intervening matter distribution. Isotropic and statistics of the CMB, again, very important, because you assume that universe on large scales is isotropic and homogeneous. That is one of the underlying assumptions of cosmology. And it has kind of shown that that is true when we look at the CMB anisotropies. And of course, there are other components. So the cosmic microwave background has actually told a lot about all the cosmological parameters and the lambda CDM model that we have discussed today. Okay. And again, this is just numbers, but I would highlight a few things. One is omega baryon, right? And that kind of tells you about the baryonic content. There is omega matter here, omega m here, which is roughly 30%. This includes dark matter, so not just the baryonic matter. And then you have things like dark energy and some things related to reionization, which is this tau. But there are lots of these parameters that one can study just from CMB, okay? But for our practical purposes, what we are interested in is the density of matter, dark energy, and radiation. And all these three information we can get from here. And of course, Penzias and Wilson did receive a Nobel Prize for their discovery of CMB. And that then led to the next stage. So before we go to the next stage, which is dark matter and dark energy, any questions so far?
Yes, sir. I want to ask, what was the first physics approach to confirm the CMB is coming from the universe? Like it is the cosmic microwave background. How did we confirm it using physics initially?
Yeah. That's a great question. And this is something that surprises me because the physics of CMB is very simple. The universe we're talking about is like hundreds of megaparsec scales, but this is essentially thermodynamics, right? So what you have is high temperature, and you kind of know what that temperature is. You have particles, which are all these standard model particles. And then you know very well their interactions because that has been studied by LHC and other collider experiments. So you know how they interact and how that rate of interaction depends on certain parameters. So what you can do is you can put all of those particles in your simulations, give the kind of interactions that they should have. So you would require, for example, interaction cross sections for each, which again has been very well studied in atomic physics. And then as the universe is expanding, you also know how the temperature should be dropped because it is adiabatic cooling. Okay. So what you will realize is slowly their interaction rates will go down. Okay. And as the interaction rate comes below the expansion rate, okay, and this is a very important statement, which is any two particles, if their interaction rate comes less than the expansion rate, then decouple. Okay, they stopped interacting because in some way expansion has taken over that. So you can now predict from just basic atomic physics at what stages of that cosmic timeline that I showed, different particles will decouple. So there are neutrinos, for example, that can decouple much earlier. Then there is photon and electron that can decouple much later, which is 400,000 years. But then there are particles in between. So you can do all that physics and find out that at this point is when the photons get decoupled, because again, you understand the photon distribution of energy, which is nothing but a Boltzmann distribution. And you know the particle interaction rates. So you can very strongly predict, and this is much before its discovery, that there should be a cosmic microwave background. And because of such strong interactions, it should have thermalized to a black body. So not only was the prediction made, but the spectrum that it should be a black body was also made.
Correct.
Yeah, please.
Okay.
Yeah, you can speak. Yeah.
Yeah. So by observing one.
Sit down.
So
Or you can speak here. That's what. Yeah, you can speak. Leave the phone. Phone the phone. Speak.
So by observing the density fluctuations in the CMB, can we confirm, the inflation has happened?
Yes. So it is an indirect confirmation of inflation. So you see density perturbations, and you know that density perturbations can be seeded during inflationary epoch, right? So this is what we call as indirect evidence. But can we directly see inflation? That is something we are still figuring out.
So I have one more question. Like when you showed the plot of CMB, there were certain regions where it showed that it is like temperature difference, I guess. Like the temperature was varying, but as it is supposed to be isotropic everywhere, why was there a temperature variance?
Are you talking about this plot?
No, sir. The CMB mapping. Map of the cosmic microwave background. Yeah.
This one?
Yes, sir. So I want to ask like what these color plots show, like where it is high, the temperature is higher and lower at places wherever it should be isotropic everywhere. Like if the thing started like simultaneously.
Yeah, no, great. So I should clarify what this plot actually represents. So just like we studied that there are density perturbations on top of a mean density, right?
Yes.
Similarly, the same thing applies for CMB. So there is a uniform background, which is 3 Kelvin, that is constant. So what we are looking at is from that 3 Kelvin baseline, how much is the fluctuation? So the red colors show that the temperature at those locations is a little higher than 3 Kelvin, which is a few microkelvins. And the blue spots represent that the temperature is a little lower. But this is all fluctuating around 3 Kelvin, which we have removed from this plot.
That is the question I have actually, sir. That why it is higher at some places, but but if initially it like began at the similar, like if the particles interacted together initially, why there is a like variation in the temperature? How did
Yeah.
like
So variation in the temperature and variation in the density are correlated. And we know that the variation in densities happened during inflation, right? We talked about over and under densities.
yes.
The same over and under densities are also imprinted on the temperature of these. So in some way, they are not independent variations. They are very tightly coupled. As a matter of fact, from the level of this anisotropy, which is roughly 1 part in 100,000, you can predict what will be the perturbation on the density also. So the source of these two are exactly the same.
Okay, so actually the CMB can take us to the inflation, how the perturbation happened during that time.
Absolutely, absolutely. So even with this measurement, as a matter of fact, I can show you one of the parameters that I kind of skipped over, which is NS, the running power law index. This actually covers some aspects of inflation. So just from this measurement, you can see a lot about what kind of inflationary models are allowed and what are not allowed. But there is still a lot of uncertainty after that. But yes, in some way, you can do a little bit of inflation from this. Yes.
What kind of uncertainty that there can be?
Yeah, because many models can produce the same anisotropies. So just by studying an anisotropy, you can't distinguish between those models. Okay, so then you have to look at what we call as polarization, which again I cannot get into. So just like temperature anisotropies, there are anisotropies in the polarization of CMB. There you have more information about inflationary models because they imprint a very unique polarization. So we have not yet detected that. There are experiments trying to, but this is all we have right now, from which we have narrowed down a set of models for inflation.
Okay, so that is.
Okay, so if there are no questions, I will move on to the constituents of universe now. So CMB was like background cosmology. And now I will talk very briefly about two different major components that we have no clue about. One is dark matter and another is dark energy. Okay, so I think dark matter may have been covered by Karthik also if he talked about galaxies. So I'll very quickly elaborate on the basics things and then move on. I want to cover dark energy a little more because that is often less talked about. So we know that most of the universe actually has dark matter rather than baryonic matter. And what we see, of course, is a fraction of that baryonic matter, right? So when I say baryonic, it is baryons, but not all baryons are luminous. What we see with our telescopes are stars and galaxies, right? So it's like this, you have stars and galaxies that you see, based on which you tell, okay, there are these baryons, but then you can't see all of them because not all of them are luminous. So then you use other probes like different lines of atoms and molecules to understand other baryons. But even that is 5%. Rest of it is dark matter. And of course, the most important way to detect this is something which is sitting right in the room where you are, which is looking at the rotation curves. Okay, and that's something I think you will probably do a tutorial on, which is when you have the velocity of the gas as you move away from a galaxy, right? So origin here is the galaxy and you are moving away from it. You will find that at some point, the velocity should have gone down. And all you have to do for this is basically at a given radius, how much mass you have, and therefore what should be the velocity if it's a centripetal force. And that should follow this gray curve. What you are seeing is completely different, right? So whether you use stars to measure the velocities or you use the gas to measure the velocities, and this is something you will do probably in the tutorial at some point, you will see that the rotation curve is vastly different. What it tells you is there is a lot of mass away from the galaxy. So the luminous matter is concentrated here, but then outside, there is a lot of invisible matter, which also has gravitational influence. Otherwise, it would not have impacted the velocity of the gas. And this was the first evidence that there is dark matter. Now, dark matter is a very loosely defined term. Anything that does not emit light can be dark, right? But we have right now very little idea about what it exactly is. So again, this is like CMB anisotropy, indirect evidence of existence of dark matter. But if you look at what could it be, the field is very much wide open. So much so that the candidates for what could constitute a dark matter start with electron volts kind of a mass, right? So we're talking about 10 raised to minus 28 to minus 31 grams. As you go up the mass, so you have something like ultra light dark matter, and there are experiments trying to detect these. You have axion-like matters, which are again very small. But then on this side, you start having even astrophysical objects that can in principle be part of the dark matter, if not completely. For example, primordial black holes. So this kind of a black hole is not coming from collapse of a star, which is the usual channel of their formation. But this is again tying up to very early universe where the density was so high at certain points that in the process of collapse, it didn't become a star, it became a black hole directly, right? So it does not need any star. And it could be anywhere between a few times mass of the sun. So a lot of people think that is what is constituting dark matter. But again, right now, we have no direct evidence of dark matter anywhere on this mass scale, from 10 raised to minus 21 electron volt all the way to 30 solar masses. Okay, so there is a huge range of what it could be. What we know for sure that it has gravitational influence. And right now, probably that is the only way it interacts with baryonic matter, which is stars and galaxies. The other means, which is electromagnetic radiation or nuclear forces, we don't think it interacts via those channels at all. And that's the best that we have right now. Okay. So this is just a thought. Yeah.
So good question here. Please ask. Yeah, you can loudly ask.
The particle called sterile neutrinos.
Yes, they are somewhere in between here. Yes. So people also think that sterile neutrinos could be one of the candidates, but based on other observations, they alone probably cannot explain the entirety of dark matter. So we know that it is roughly what, 27% of the universe. It's difficult to explain that by a single constituent. So
But
now a group.
Experiments explaining that neutrinos do exist, like the super K experiment.
The neutrinos do exist, of course, but are those neutrinos constituting dark matter is definitely not clear. So neutrinos, of course, have neutrinos. As a matter of fact, when you look at the cosmic timeline, they came again within a few seconds of Big Bang, and their presence has been, of course, unanimously confirmed. Their position as a dark matter candidate is not so. Okay. So there are lots of candidates and there is active experiment. And as a matter of fact, different kinds of experiments catering to different ranges of the masses. Okay. But as of today, we do not have a direct detection of any of these particles as dark matter. So this is where we are in this field, which is 27%. And if it is a little sad, then I'll go to dark energy, which we have even less idea about, and that is 70%. Okay, so you will suddenly feel better about dark matter now. Okay, so dark matter had much earlier origins, right? So we are talking about going back to Hubble. Okay, and what he saw was how the velocity of the different objects was as a function of distance from the Earth where he was observing from. And of course, that basically led to our most widely model that we use now, right? Which is the velocity was proportional to the distance. And that's how we came to kind of conclude that the universe is expanding. So farther the object, faster it's moving, which is basically, though I should say it was very bold of him to fit a straight line through this plot. But it turned out that it was a correct assumption, because later when we had more accurate data, it actually fits well. Okay. But on the theoretical side, it was none else but Einstein who proposed that there might be component in the universe which was accelerating. Okay. And he introduced a term of lambda here. But then he also kind of retracted over it. And he says here that the cosmic repulsion idea was the biggest blunder he had made in his entire life. So because back then we did not even have evidence that there could be something in the universe that can be repulsive and it could work against gravity and accelerate the expansion. This was a purely theoretical idea. For example, in the Hubble's case, it was not clear it was accelerating. It was only clear that it was expanding, and there is a difference between the two. So he retracted it, but looks like he was not wrong in terms of introducing a lambda term, because we have now several evidence from CMB all the way to what we call as supernovae that the universe is not only expanding, but it is also accelerating. And if you only have dark matter and baryonic matter, you cannot explain that acceleration, because these matters are gravitationally attractive. They will always want to deaccelerate the universe, not accelerate it. And the way to do that is actually, well, in theory, very straightforward, but it actually is very nuanced. You look at objects at different distances from you. Okay. So the x-axis here is redshift. Redshift is nothing but the distance of object from you. Now, what you also want to look at is how bright they are, which is the y-axis. Okay. So higher the number, fainter is the object. And of course, what you would expect is the distant objects would be more faint and the nearby objects would be much bright. Now, you can use this to then see or calibrate that to see, okay, what is the distance? So this magnitude here that you measure can be converted to distance. And this is only possible if you know intrinsically how bright is the object. So I take a candle, I lit it, I measure the flux that's coming from the candle. Okay. Now I place it 1 kilometers away. Because I knew how bright it was when it was close to me, I can measure that it's at 1 kilometer because I see how faint it is now. The same standard candles are used, and supernovae are one of the most dominant candidates for measuring that. They are what we call as standard candles. So we kind of understand how bright they are when they become supernovae. And therefore, you can use that to get a plot which is shown on the right. So distance is a function of redshift. If there was no dark energy, it would follow this line. And what you see is line. It's still a straight line, but it is away. It's not the same as no dark energy line. Okay. And this is one of the best indicators that the objects are much farther than what they would be if there was no dark energy, right? Because these all objects will come down, which means that their distances are lesser. But they're farther means there is something which is pushing them away from this line. It's pushing them farther. And this is in some way the evidence that there is dark energy. And not only that, you can do different kinds of model fitting and find out how much dark energy do you need to shift them like this. On this scale, they're very small, right? But this really needs 70% of dark energy. And adding even more desperation here, theoretically, we are unable to explain this. So the theoretical estimates of dark energy are 10 raised to 120 times higher than what we measure. Okay. And this is widely considered as one of the most discrepant measurements between theory and observations. So in some way, dark energy continues to be a mystery. What we know are two things. It is roughly 70% of the universe, and the fact that it works against the gravity. It repels things instead of pulling them together. And that's why universe is accelerating. That's about it. Now it's a little disconcerting that we don't understand anything about what it is really. So there are experiments that are trying to do that. You could, for example, look at the galaxies and trace their positions and how they are moving. So that is something which is done by experiments like DESI. So this is dark energy spectrograph instrument, and it had a fascinating result just a few months ago on the first dark energy estimates in the universe. You can also do that by radio telescopes, as a matter of fact. And experiments like CHIME, HIRAX, and other experiments are trying to study that. And of course, I can't get into the details of this, but the idea is that you are mapping the hydrogen that is available in the universe, and in some way you are using them to understand how the galaxies are distributed, because most of the hydrogen will reside inside the galaxies. So you could use that kind of a technique, what we call as intensity mapping, to also study dark energy. Okay. And of course, again, Nobel Prizes, this whole discovery that the universe is not only expanding, but it's also accelerating, led to a Nobel Prize. Adam Rees is right here, Brian Schmidt is here, that led these efforts of using these supernovae to constrain dark energy models. So I have covered almost all the constituents, and I will probably take 5-10 more minutes and finish off the last part of my talk, which is the first stars and galaxies. But before that, two things to the students, if you had any questions till now, and from Prabhu, how much time have I now?
I think we are relatively okay with time, Saurabh. You please take your time. They will only have to take the after some time.
Sir,
Okay.
I have one more question.
There is one more question, yeah, please.
Yeah, so sir, you said initially the universe was deaccelerating, and at some point, like the dark energy came, and then it started accelerating. So, like, when was the time that dark energy came, and like they don't know about dark energy, so we cannot explain how it came, but we can say like when was the time it came, right?
Wonderful. So I want to refine what I said, which is it's not that dark energy came and at some point later and then started accelerating the universe. Dark energy has always been there, okay, right from the initial time. So that's why even with the CMB measurements, this is much before the stars formed, much before the galaxies formed, we can estimate dark energy actually, okay? So dark energy was always there. The expansion of the universe is driven by what is the most dominant component. So what happens is you have some mass, matter, omega m, you have some radiation, omega gamma, and then you have dark energy, which is omega lambda. Okay, so these are the three major constituents. Now, what happens is initially the omega m, which is the matter contribution, was very high compared to omega lambda. Now, omega lambda, the problem is, or I don't know whether it is a problem, but it is constant with time. It does not change. So omega lambda, if you plot as a function of time, it's a flat line. Omega matter, on the other hand, falls with time. And that is understandable because universe is accelerating, so your densities are going down. So now you imagine there is a flat line. There is omega m, omega matter line, which is starting above, but at some time it will cross over this flat line and come down. That crossover is when we think dark energy took over, right? Because it was constant. And that happened very recently. We are talking about redshift of 1. And just to give you a context, CMB happened, we are at 0, okay, redshift 0. And cosmological redshift is nothing but an indicator of distance for now, or time, they are intertwined. But anyway, so CMB happened at 1100 redshift. We are at 0 redshift. Star formed around redshift of 10 and 20, right? So already stars and galaxies were there. We are talking about redshift 1, which is relatively very recent. As a matter of fact, Earth had already formed around this. There were bacteria on Earth when dark energy took over. So, in some way, it's a very recent phenomena, and it is very exciting to see cosmology playing out such big roles at so recent times. Because in cosmology, we often think about the history, but here these time scales don't match. So, dark energy has always been there, just that it became the most dominant component around redshift 1.
Then it became more dominant in that time, recent times. But since when was it there? Like, that's what my question is. Like, since the beginning, since
yeah,
the
yeah,
Big
yeah.
Bang, or after the formation of stars, or when? When was
Yeah,
it?
no. It was there since the Big Bang. So basically, in this timeline, I would put it right here. So in some way, it's not that dark energy came at some point, dark matter came at some point, baryonic matter came, photon came. All of these 4 things, radiation, baryonic matter, dark energy, all 4 are here right in the first slice. And then all of them are co-evolving.
So then I have, please ask another question here, Saurabh, please.
Sir, as you mentioned, the matter domination, if it is constant, then going on with the time, is the proportion of the dark energy and dark matter can increase.
Dark matter not, because dark matter, so when I say omega matter, it's both dark matter and visible matter. But yes, the impact of omega lambda, which is dark energy, it will continue to be wider compared to rest. Rest are falling. So omega lambda in some way will get more and more dominant. So there is always this open question of how the universe will end, right? Will it continue to just expand and then at some point just rip off the atoms also at that level? Or at some point it will stop expanding and start contracting, what we call as big crunch. Okay. Right now, again, there is no way to know, but people are studying, for example, if omega lambda also changes with time. And there are some tentative indications that there may be something there. Again, it's all very dubious. But in case if omega lambda does not change with time, if it continues to be constant, we are up for eternal expansion.
Sir, can you tell us the reason, elaborate us on why cosmological constant lambda is comparable to the matter density today?
Okay. No, I could understand. No, I could hear, Prabhu. No problem. Yeah. It's, well, comparable as in 0.3 versus 0.7. That is the number. So let me go to the CMB table here. Right. So omega m is 0.3. So essentially the way it has been normalized, and again, I can't get into the details, but the idea is this is density in a fractional way. So all of that should add to 1. Okay. So there are 4, as I said, omega m, which is matter, which is visible and dark matter both. There is omega lambda, which is dark energy. There is omega gamma, which is radiation, but radiation plays a very insignificant role. And then there is something called omega k. I have not talked about it and I will not talk about it. It's about flatness of the universe. And for all practical purposes, what we know is universe is flat. Okay. Though it has no reason to be. It could be curved. But anyway, the point is the sum of all these 4 should come out to be 1 by construction. This is how we have defined them. So omega matter is 0.3 and omega lambda is roughly 0.7. So I wouldn't say they are very comparable simply because the sum is 1. But yes, at some point they were comparable, and that's when the omega lambda took over. And that comparable thing happened simply because omega lambda was not changing while omega m was reducing with time. So at some point they had to intersect. Any further questions?
Many questions. Let's try it. Yeah, there's one more question, Saurabh.
Yeah, go ahead.
A couple more, yeah.
So, like,
Okay.
when we were discussing about dark matter, so we saw the ratios, like how much it's varying, and like the maximum that contributed to it was ultralight dark matter. So, can you explain a bit more on that? And like, it's the major portion. So, if we find anything regarding that, so it could compromise the maximum part of it. Is that so?
It could come maximum. Okay, you're talking of, so this in scientific terms we call it abundance. So essentially, yeah. So if, for example, the dark matter is of the nature of ultra light dark matter of this range, yes. If there is a direct detection, and that itself is a big deal, it can in principle explain the abundance of dark matter, right? Having said that, what I have not shown on this plot is there are constraints on some of the mass ranges. Okay, we have, because we have particle physics experiments, right, which operate at a range of different energies. So some parts of this mass scale has already been constrained, and by what I mean by that is no particle interactions have been detected in that range. So that also puts some limit on which masses are allowed, which masses are not possible. So yes, if we go towards the particle side of dark matter, which is the left side of this, it is possible that they can comprise the entirety of dark matter. But when I go to the right side of this plot, in particular astrophysical objects like primordial black holes, there are more constraints coming not from particle physics, but from astrophysics. We have been able to see a lot of galaxies, lot of lensing experiments, supernovae. All of these put a constraint that, okay, if dark matter candidate, say primordial black hole, was of astrophysical origin, it cannot be more than this abundance. So there you have to mix other components also. Okay. So in some way, both from particle physics and from astrophysics, you have some constraints on the masses of this.
Yeah, one more question, two more questions, sir.
Sir, I want to go back to the statement that when the matter domination, on the dark matter, you said no, it is at some point of time, it doesn't change, right?
Yeah.
What we want to know, I want to put a spotlight on, then we say, the new stars are formed, new things are formed, then how do we say, the matter domination is same? How do we say?
Yeah. Good. No, that's a very good question. If dark energy is the expansion causing thing, then why do we have formation of new stars? Is that the question?
Sir, you told that, the matter domination is same, quite same, right? Matter, omega m, I guess.
Omega m changes with time. Omega lambda, which is dark energy, remains constant.
Okay.
So the reason for that is, for example, if dark energy is expanding, why aren't we moving away? And the simple reason is that these things apply at cosmological scales, not at human scales or galactic scales. So for example, dark energy will not let sun and earth drift apart as of now, right? So there are different scales in astrophysics, right from human scales, planetary scales, galactic scales, extragalactic scales. So when we talk about cosmology or any of this, dark matter, dark energy, we are talking about extragalactic scales. So a typical number to keep in mind is a few hundred megaparsec. Okay. About a few hundred megaparsecs here.
Yeah, please ask Deepan.
Sir, I might have missed it when you explained it, but you said that when the universe was 10 billion years old, dark energy started dominating. But how did we come up with this 10 billion years old number? Like, how did we come up with this fact?
Yeah. So this is coming mostly from theoretical interpretation because just from the background cosmology, omega m, which is the matter and dark matter, and how it changes over redshift. So I have not formally introduced the redshift term, but redshift in some way is proxy for time. Okay. Now, how to convert redshift into time depends on the cosmological model. So we will only talk about redshift. So omega m, for example, suppose it goes by 1 plus z, z is the redshift cubed. Okay. So we know what is omega m at CMB, which is coming from the measurement of these anisotropies that I talked about here. So using these anisotropy right here, you can estimate the value of omega m. Okay. So having established that, you know how it is evolving with redshift. It's basically reducing with redshift. Redshift means when we see it from our side, it is less. So just mathematically, you have say omega m times 1 plus z cube or divided by 1 plus z cube, which is how this is evolving with z. and on the other side, you have omega lambda. So all you have to do is equate these two terms and see at what redshift they become same. So this is just an algebraic expression based on which you kind of estimate it is around 1. That number itself comes around 1. The question is, have we observationally seen that? I wouldn't say that there is a very explicit time that, okay, this is the time at which the expansion rate took over. But as you can see from here, this plot goes from 0, where we are, to 1, which is what I was talking. There is imprint of dark energy throughout. So we know that the dark energy started playing a role even before. Right now, we don't have a lot of data to extend this. Ideally, we would want to extend x-axis all the way to before dark energy took over, exactly what you were asking, right? So we probably think that at redshift 3, it may not have played a dominant role. So there, it will start falling here, right? But we have not seen it simply because we are right now sensitivity limited. So we have only seen things where dark energy is a dominant this component of this universe.
Yeah. You have some. What about anyone else? You have one question. Can you come here and ask? No. There is one more question, sir. How do we know that dark energy is like 74% of the entire universe?
Yeah. 2 ways to know. One way is what the plot is. So you can write down an equation that translates the redshift to distance. Okay. And from the observed magnitude, you get the distance. So now distance and redshift have a relation. That relation also has omega lambda. Okay. So what you can do is a basic typical curve fitting. You can change omega lambda and see at what value of omega lambda this fits perfectly. Okay. And this is actually, this data is available in public domain. You can very much do it yourself. Okay. And you will find that you need omega lambda of around 0.7 to be able to fit this data. Omega lambda 0 will not fit it very clearly. Okay. So that is one way. The other way is coming from the CMB. So if I go back to your anisotropies, which is this, you can make a power spectrum out of it, which is this, where you are looking at how the power is correlated at different angular scales. And this angular scale, if you write down the mathematical expression, will also have omega lambda omega matter. And what you are seeing, actually the green line is a fit. So using this fit also, you can estimate omega lambda. So in some way, if I go back to my timeline, one estimate of omega lambda is coming from our very local universe, from this second last slice, and one measure of omega lambda is coming from this slice. So in some way, you have multiple ways to say that there is dark energy. And in some way, the next part is slightly different. Till now, we were only talking about the dark part of the universe, which is dark matter and dark energy. The last part is the luminous part of the matter, which is stars and galaxies. Okay. And this is something that we probably understand a little bit better than those dark things. See? So formation of first stars and galaxies, from that slice, if you remember, it was roughly around a few 100 million years after the Big Bang. Okay. And they followed the dynamics that was governed by dark matter and dark energy in some way. But what happens is, what we had started in the beginning, you have overdensity. Those overdensities collapse. At some point, they start forming stars, which finally groups and makes galaxies. And there are several galaxies. So the last part actually is very close to my heart, because that's what I do, to understand how the first stars and galaxies formed in the universe. Now, the reason this is very important is when you want to form a star now, suppose I want to form a star in my galaxy, in the Milky Way. Okay. Of course, I need hydrogen gas. That is the primary ingredient. But then what happens is, when you collapse this gas, it gets heated up. Okay. So you also need something as a radiator, something to dissipate that heat so that it can then collapse more and more. Otherwise, it gets stalled. And this is very well studied in the local universe. And the best radiators are nothing but molecules. There are several molecules that can, with their transition lines, radiate the heat out and allow this gas to further compactify to be able to make a star. Now, based on your earlier lectures, where do these molecules come from or heavy metals come from?
Reaction happening.
Sorry?
Reaction happening in core of stars.
Could you repeat that again? There was
In the core of stars, yes, I heard.
Yeah, fusion reaction happening. Right. Okay.
Yes. So core of stars can, yeah. So initially universe is hydrogen, helium, trace amounts of lithium. And then when the stars form, in their core, you can make elements till iron. Okay. Unfortunately, after iron, the stars cannot make any more elements because the core collapses. Okay. So how do you form elements beyond that?
That happens when the star dies and like it explodes. That supernova during supernova.
Wonderful. That's the answer I was looking for. Most of the heavy elements are produced in supernovae. Now, so it's like this. You need heavy metals to form stars, and the heavy metals are formed from supernovae, which are formed from stars. So now you see the problem. Chicken and egg, which came first? So there were no heavy metals when the first stars formed. So their formation is really a mystery. And that is just one reason why we want to study them. Okay. And there are other reasons. I'll come to that. So we expect, as I said, roughly a few 100 million years after Big Bang, we had the first stars. And slowly they started forming these galaxies, which then merged and into bigger structures, which finally led to what we see today. Now, these first stars and galaxies did transformational things. They emitted a lot of radiation, both as X-rays that heated the gas, and you will hear a lot about X-rays in your second week. And they also emitted a lot of ionizing radiation, right? And that also ate up a lot of hydrogen gas in the universe. So much so that by roughly 1 billion years after Big Bang, which is roughly here, there was no hydrogen left. So all the hydrogen which was present between the galaxies was fully eaten up or ionized by the radiation that was emitted from these galaxies. That is what we call as epoch of reionization, EOR. Okay, so the stars form here around a few 100 billion years, and by 1 billion year, the radiation from them have depleted all the hydrogen gas. So the universe that we live in now only has hydrogen in the galaxies, like Milky Way has hydrogen. But in between the galaxies, for example, between Milky Way and Andromeda, you will not find anything. So this whole span from the formation of first stars to the end of reionization is very poorly understood, simply because you don't have powerful telescopes to be able to see them. Okay, so this is a very open problem. What was the nature? And there are several questions that we want to ask. For example, you could ask, we look at sun. The sun is a more recent star. How were the masses of these first stars, which is here in purple, compared with the sun? Now, if you ask this in a conference, it will create a riot because people, you will see papers on both sides. There are theoretical models that predict that the first stars will be much massive than the sun. Some papers say no, because the channel of formation was very different. There were no heavy metals. So we still don't understand that. Similarly, luminosity. We kind of understand for today what kind of luminosities are expected out of these. But then how luminous were the first stars? We don't know. How they exactly ionized the universe from their UV radiation? Again, we probably don't understand well. And then how long did they even live? Usually more massive the star, shorter it lives. But then compared to a lifespan of sun here, which is shown in the orange, we don't quite know it because we also don't know the masses. So these are some of the questions, but there are a lot more. For example, when did they form even? We don't know. So there are various reasons to study this particular slice, which is around 400,000 years ago after Big Bang, about the stars and galaxies. And the way we are doing that here, particularly at RRI, is not by looking at stars and galaxies directly, because there is no way you can see them. Even most powerful telescopes like JWST that I showed earlier, it cannot go to these distances. So we are talking about such early stages of the universe that these galaxies, particularly the dwarf galaxies, they are too faint, so they cannot be seen directly. Instead, what we are trying to do is to be able to measure them using 21 centimeter radiation. And I believe 21 centimeters, some part has been covered in the earlier lectures. Is that right?
Yeah.
Okay.
Sorry.
Yeah. So now, usually when we do these 21 centimeter radiation detection experiments, we mostly focus on hydrogen in our galaxy, which is what you will be doing. But here the challenge is to be able to see that at very distant galaxies, which are at very high redshift. And of course, this is a picture just to show that on the right. A galaxy in the optical, which is mostly looking at the stars, will be much smaller than the 21 centimeter, because 21 centimeter captures the hydrogen distribution. And we know that not all the hydrogen has gone into making stars. So a galaxy on the same scale will look much wider. So this has been done. This has been done in local universe, but we want to do that at very high redshifts. So in terms of cosmological redshifts, we are at 0. CMB is at 1100. These two numbers we should know. We are looking at redshifts 10, around 10 to 30 for understanding the first stars. Now, the highest redshift at which we have detected 21 centimeter is 1.4. Okay. So beyond 1.4, we never have a detection. But here with our experiments, we are trying to do this at redshifts 10 and beyond. So it's a huge leap of faith again in how to do that. And it is a very challenging exercise, something that Mayuri will talk about tomorrow. But I'll skip all of this and very quickly cover the kind of challenges that we have. And that's the reason we are here at Arctic, which is when you try to study signals from these first stars using the hydrogen gas particularly, by the time they come to us, they reduce in their frequency. So 21 centimeter is the wavelength, as you know, which corresponds to a frequency of 1420 megahertz. By the time it comes to us, it is redshifted thanks to expansion of the universe. So we are talking about frequencies of a few hundreds of megahertz, okay? Roughly 50 megahertz to 200 megahertz. Now the problem is all of these intervening things. We have galaxy, we have other galaxies, we have ionosphere, we have human-generated interference. All of this forms very much part of your data. So, and all of these things are much, much stronger than the first light signal, which is the 21 centimeter signal. Okay. So you have data where you have added everything, and now you have to subtract every single thing, whether it is human-generated interference, your own telescopic contamination, ionosphere, galaxy, all of this, which are roughly 100,000 times stronger than the signal. You have to remove that to get back to this. And that's where the challenge is. Okay. So we need to build telescopes which are accurate to 1 part in a million, which is something we are doing at RRI. And we have essentially 2 experiments. The first experiment is SARAS, which is ground-based experiment. It has 1 antenna, which is a monopole right now. As you see, it floats on water for various reasons. Right now, it is kept on the snow. I wish I could show you a picture, but I cannot. I don't have that. But it can operate in different kind of regions, and it can collect data. The other experiment that again you will hear more about is Pratush. It's basically an extension in the radio quietness. So we keep going to these remote locations, and Girish, Saturday we'll talk a little more about SARAS and its different deployments and different field experiences. But the best field condition is far side of the moon, because that is something which is completely shielding the Earth. We never see the far side of the moon. So all the terrestrial radiation from Earth, these are FM transmitters, the digital TVs, the satellites, solar panels, electronic devices, LED lamps, I can count on and on. All of them are blocked when you have a telescope that is behind them. So our eventual goal is to have simultaneous observations where SARAS has to go to these very remote areas because there the interference levels are low. For example, Arctic here. But we also eventually have to move out of Earth's atmosphere and go to the far side, which is the most pristine location to be able to do any of these studies for the first stars and galaxies. Okay. So with this, I think I will stop. Tomorrow, you will hear more about these experiments, what they are doing, how they operate. And then with Girish's talk, you will know a little more about how to deploy this and what kind of challenges are involved in this. Okay. So I'll stop here and I'll take questions on my last part and also overall questions you have on these talks. Thank you.
Sir, I have a question. So, like, I missed the part when you said that the stars would have formed because of the heavy metals. Like, if the heavy metals were present, only then stars would have formed. So we do not know how initially they formed. So, like, why is that? Like, why do we need only heavy? Why do we need heavy metals for the initial star formation?
Yeah, the reason is we have to see how well they can radiate the heat out. Because in the process of star formation, you will always heat the gas. And so now you have two forces. One is because of this heat, there is pressure which is trying to throw it out. And then there is gravity which is trying to push it in. So at some point they reach equilibrium. And when that equilibrium is reached, you can't collapse it more. So now the question is, if you have only hydrogen, does it have those transitional states that can radiate the heat outside this collapsing region? And based off our knowledge of hydrogen, it's a little difficult. It's not that it's impossible. And we know it's not impossible because first stars did form, because we exist. But we kind of don't understand that channel. While for heavy metals, because they have a number of vibrational states, transitional states, that they have more ways to radiate the heat out in terms of different kinds of radiation. So in local universe, it is almost inevitable that you will form stars in the presence of heavy metals. You may have heard about molecular clouds for that matter. These are the seeds of star formation in the galaxy. They are extremely cold places, 10 Kelvin, for example, and they are rich with these metals. So you very readily form stars there. For stars, the only way of cooling that is hydrogen. And we for sure know that's not a very efficient way. So not impossible, but it is challenging to form.
So, like, is that possible that somehow before the formation of stars, the heavy metals might have formed at some places?
Yeah, right now we do not know of any channels that can form those outside supernovae.
But sir, the experiments are happening which are trying to generate heavy metals using the collisions.
So supernovae is like a collider experiment, right? So what you really need to do for formation of these is collide particles with very heavy energy, right? So LHC does that artificially. Supernovae does it naturally because the amount of energy which is released in a supernova is very high. So the question is, before the stars had formed and therefore before supernovae occurred, were there energetic processes that could make this collision happen?
So there can be an energy which could have caused that. Like there might be some energy, like the energy which made them collide.
So that's a hypothesis. I mean, theoretically, yes, if there is a source of energy that can make particles collide, it can form heavy metals. But as of today, based on the data that we have, we do not know of any such channels. Yeah, but theoretically, that is possible.
Yeah, another question. Yeah, please, correct.
Sir,
You have finished or? Sorry,
Sir, I have a small question about Saras. We know that Saras has been deployed in the low RFA regions, but I want to know how do you guys tackle with the instrumentation effects? That might bring a dip in the curve you are plotting.
Absolutely, yes. And that I would say is the bottleneck, because to some extent you can tackle the RFI. That is fine. And in Saras, for example, there are a lot of instrumental effects, and not just Saras, in general, any experiment. So to name a few, you need to have a primary beam with a given antenna. You need to have an impedance that is changing with frequency. Then you need to have bandpass of your system. So the point is, we have to design these experiments so that these kind of effects are minimal in the data. So for example, when we design antenna, we want to make sure that its field of view doesn't change rapidly across our frequency range of operation. So that reduces a lot of systematics. Similarly, the entire thing, as you can see here, is the entire receiver is sitting below the antenna. So we want to minimize any long lens because even that can introduce a lot of artificial features. So we have taken careful consideration in miniaturization, in the way you calibrate for the system, in the way you design your antennas, so that your telescope contamination at least is less. And therefore, it makes sense to go to these regions to then also reduce. Because if your telescope contamination is not reduced, no point going to other locations. Yeah.
Sir, but here, deploying in the Earth is okay, but having the payload in the Pratyush, what about that? Because the whole payload is inside now. So there might be some more effects on the side of instrumentation. So how do you guys tackle with that?
Absolutely. That's a brilliant question, which is, of course, we are reducing one challenge of interference, but now we have more challenges for instrumentation in Pratyush. That is something you will hear about it in more detail tomorrow. But the short answer is, and that's why Pratyush is not a replica of Saras. You can see the designs are different. And the reason is because now, unlike in Saras, where you have a digital receiver very far away from antenna, and that the reason is simply because you don't want that extra interference from your system to be picked up here. In Pratyush, everything is just below the antenna. So then you need to have more shielding. There needs to be materials that can absorb that radiation within the satellite and not leak it to the antenna. Then the antenna itself, you can see its profile, so that the impact of the satellite on the antenna is very small. So there have been these redressal measures we have done on Pratyush to basically counter for the extra challenges. And I should say this is a work in progress. There is a lot going on right now. When you go to RRI, you will see the lab model of this and the kind of considerations we have put in to basically eliminate those instrumentation effects. Yeah, it is more challenging for sure.
Sir, a small hypothetical question. Sir, do you guys take account of the cosmic rays so that you plant it in the space in the time of high solar, activity to get rid of the effect of the cosmic rays? Do you have? Do you take account of that?
No. So the point is these satellites, and more than the payload, it's the satellite electronics that is very susceptible to cosmic rays. So in the process of very high activity, what is usually done is satellite is turned off. So that your instruments are, we don't have a way to subtract it in the data. We simply don't observe.
But I have a question. Yeah, it's one more question.
Sir, I'm not sure, but some years before, I've heard that there are galaxies even older than our the observer. Like we know that the universe is 13.8 billion years old, but there are even galaxies which is even older than 13.8 billion years ago. Then, sir, how could it be possible? Like if there are galaxies even older than universe?
Yeah, no, that's a good question. And that is something I was not trying to get into because of the lack of time, but thanks for bringing it up. So JWST has been observing galaxies, a lot of them. And though it has not really reached the first stars, so I'll go back to the timeline now. It has not really reached that slice, which is 400,000 years, which is right here. Yeah, so it has not reached here, but it is somewhere in between, maybe somewhere here. Okay. It is kind of touching the 1 billion years from the Big Bang boundary. Now, even there, we did not expect such massive and luminous galaxies. And of course, any optical telescope will selectively observe or detect the galaxies which are very bright. It will not be able to observe faint galaxies. So at this slice, around 1 billion years, it is picking up very bright galaxies. It's not to say that all the galaxies are bright. There are galaxies which are very faint, which it has not detected. But even those bright ones, we did not expect. And that's what has led to the question that you asked, that what if our universe age is misinterpreted or miscalculated? What if galaxies have been there for very long so that they had sufficient time to become so massive and so luminous? Okay. So all you are doing there is extending this timeline to left. Now, I would say that's a not widely accepted hypothesis because we have very robust and very accurate estimates of the age of the universe. So it is very difficult to change the age. We cannot say that instead of 14 billion years, it was 28 billion years. That is going to violate a lot of other observations like CMB. Now, within that 14 billion framework, you cannot have galaxies clearly older than the age of the universe. So then you have to look at the astrophysics of how the galaxy is formed. And is it possible for you to produce galaxies which are very massive in the very early stages of the universe? Again, it's a very open problem, but the consensus right now is if you understand the galactic formation process as well, including some of the feedback processes that Karthik had probably talked to you in his simulations, you can in principle produce very massive galaxies at high redshifts also. And right now that is the most widely accepted model.
Then I have one more question. Like we read about, like we observed CMB, and after that, the things are happening after inflation and all. But how are we quite sure that it was 13.8 billion years ago? The universe was formed 13.8 billion years ago. How are we quite sure about that?
Yeah, I would say the most important measurement for that is none other than the CMB. Okay. So in some way, it's a storehouse of information, really. So this power spectrum that you see is very non-trivial. And one of the parameters that gets into this when you fit this is age of the universe. So in some way, you can estimate age of the universe along with the densities of matter and dark energy just with this. Having said that, there are now even local universe observations like supernovae and other things that can help you estimate age of the universe. And that is, of course, related to Hubble constant, something I did not have time to get into. But in some way, now there are multiple observations, both from the early universe, which is cosmic microwave background, and from the late universe, which is these supernovae and other very luminous objects, based on which we have kind of arrived at this consensus that universe is 14 billion years. So just because JWST has observed a luminous galaxy at high redshift, it's very difficult to change age of the universe based on one observation.
But he's asked. Let's start. Saurabh, I think,
Any further?
yeah, maybe one. I'll have one more question, Saurabh.
So, like we said that there is a timeline you shown that supports the idea of universe being found before 13.8 billion years ago. But why do you support the idea that universe has a start? Like, why is that starting point there?
Yeah, good question. So there were competing models. So for example, in the 60s and 70s, there was one model called steady state universe, okay, which was like a competitor model to hot Big Bang, which is what I am talking about. So that's why I started with this timeline saying that this is one of the models. This is not the only model. So usually like in science, for example, what happens is you have 5 models and you have different kinds of observations. You have CMB observations, you have supernovae observations, you have AGNs, you have quasars, you have different kinds of observations across this timeline, okay? So the question is, under a particular model, which kind of a model consistently explains all the observations without contradicting anything? So it's not that one particular model said, okay, universe had a beginning or a Big Bang. It is a combination. And it started off really with the Big Bang observation, this CMB observations in the 65. Because in a steady state model, there is no concept of having anisotropies in the CMB, for example, because universe has always been like this. That is the steady state universe. So in some way, there would be these competing models, but the short answer is this particular one satisfies most of the observations. So if there is a model that can tomorrow be better explained, we will definitely adopt that. So this is something that we have to keep on testing and changing.
Yeah, please. Can you share your name and ask the
My name,
Yeah.
so my name is Suraj. So I have a question. So we said that every black body is a good absorber and a good emitter as well. So sir, in case of black holes only observe. How can we apply the black body concept that every black body absorbs as well and emit as well? So here black holes emit, like what do black hole emit here?
Yeah. No, so I think these are two different things and we should not confuse. When we say black body radiation, we basically mean a system which is completely equilibrated. So you have matter, you have photons, they are in equilibrium, and therefore there is one number, which is this one temperature that explains the whole system. So that is what we call as black body. So CMB, for example, follows a black body spectrum. The black holes are not related to black body. So black holes essentially are when the massive stars die, the core part of that star, which is left behind, is a region of very high density. And therefore, the escape velocity, which you may have worked out, it is square root of 2 gr. You will find that that is higher than the speed of light. So by construction, because its escape velocity is higher, the light itself cannot radiate or it cannot escape. So that's not related to black body. Black hole is called so simply because it cannot, by construction, radiate anything. Okay, so these are two different things.
Yes, sir.
Sir, one more question, last question.
Yeah. Name and ask if you
Sir, I'm Shruti, and I have a question that after inflation, you explained that initially there was plasma, but the particles formed later. So how the plasma was there, like how the ions were there initially?
Yeah. Oh, so then that picture of plasma also I should refine. So yeah, again, the sequence of plasma particles, photons, they are not sequential, they are parallel. Okay, so
Can you
basically,
repeat again, sir? I couldn't understand. Like I missed the point of the point you said. Just I missed it. Can you repeat it again?
I'll repeat. So this sequential nature is not the right way to think, which is it's not that when the inflation ended, you had plasma and then electrons and then photons. It's not like that because in some way the particle production started right there. So when I say plasma, all I mean is very energetic photons and very energetic particles very tightly coupled. That is plasma, right? So in some way, it's not that plasma happened and then particles formed. Right at the end of inflation, because of the high energy, high density, they formed at the same time. So they formed and constituted plasma. That is the right way to put it.
one more question, two more questions. Saurabh, we have time. Will okay?
Yeah, go ahead.
Yeah, please go on. Your name and ask.
So I am Sandeepan, and this might be a little out of the topic which we discussed today, but can you brief tell us about what is our understanding of FRBs and how it poses a challenge to the cosmological things which we study?
Okay. Wonderful. Prabhu, since he brought FRB, I was thinking instead if I should give a talk on FRBs, but anyway. I cannot get into the details of your question. I think I may require another talk. I'll give you a short answer. Right now, FRBs do not contradict cosmology. Okay. As a matter of fact, using FRBs, we believe we can actually do cosmology at some point. Okay. Now, FRBs itself, so for people who don't know, this is fast radio bursts. And for that matter, I may have one slide on FRBs because from my last lecture in RAS, there was something. Okay. So these are basically luminous objects that go off. And these are mostly outside the galaxy, outside Milky Way galaxy. And they exist for a few hundreds of milliseconds to 100 milliseconds, and then they die. Okay. They just disappear. And this is a very recent discovery, relatively 2007. So what you see here is this FRB, which just turned on, turned off. Okay. So this was the first discovery. And since then, we have had lots of discoveries all across the different regions of the sky. So they are not coming from one direction, they are coming from everywhere. So we don't know what causes them. That is first thing. But then based on their what we call as dispersion measure, something maybe Prabhu or others could tell you a little more better than I can. But the idea is it will tell you a lot about the electron content between the galaxy it has come from and your own galaxy. So the cosmology part of FRB is that if you see many of FRBs from different galaxies, it can help you map out how this intervening medium, the electron distribution, is there around our galaxy. So that is the cosmology aspect. But so far, nothing in FRB has violated any cosmological principle.
So one more question, sir. I am Pranav. So while you were explaining one of our students posted, who said that while discussing about the age of the universe, isn't it? So at the time you told that you for correctly interpreting the age, there might be still some reworks will be needed in astrophysics side for guessing the how the galaxies have been formed. So what got strike me is that so if we reworked on the formation of galaxy part, can we answer the question or contradiction? Or you have said you have mentioned the during the lecture, no, sir. So heavier elements will be formed during supernova explosion, but the stars which are formed needs heavy element, but we don't know how it gets formed. So can this rework or in rework can secretly answer these questions?
It can very much so. So we do feel that if we are able to detect this 21 centimeter signal from the first stars around this slice, it can in very strong ways complement with what JWST is saying. And I can give you one example, which is when you look at a galaxy, you really don't estimate mass of the galaxy because what you see is light. So you know the luminous content. And then from the luminous content of the galaxy, you go to the mass. And there is a relation that we have derived from the local universe. And I don't know if Karthik had time to explain you this, but the conversion of how the hydrogen is getting into the stars is very non-trivial. And this is something which is called star formation efficiency. So in the local universe, that star formation efficiency is very low. We are talking about 2%, 3%. So within a galaxy, only 2-3% of the gas actually gets converted into stars. Rest of it stays neutral. And there are reasons for it. We'll not get into it. So now when I look at the galaxy, I know I'm only looking at the stars part of it. So then I use this relation to construct the mass of the galaxy. JWST is looking at very different times. It's looking somewhere here, right? This slice. So one way to counter this observation is to say that maybe in early universe, you had lot more star formation efficiency. That is, a very big chunk of hydrogen was getting converted into stars. And that can in principle explain those observations because now when you go from the luminous content to the mass, your scaling relations are different. So using logic like this, you can in principle explain JWST. Now, from 21 centimeter observations, from the very same slice, the first stars, you can independently estimate star formation efficiency. So now, if you're there also, you're getting star formation efficiency of say 100% or 90%, and JWST also is consistent, then these two observations together will point a very self-consistent picture.
I have a question. So we say the space and time came into existence due to the expansion of the singularity. And we know that the universe is even expanding right now. So it is expanding into what thing, sir? Outside of this universe, is there also like a kind of another kind of a space into what it is expanding?
Yeah. Unfortunately, I don't have an answer to this. So the thing is this, all of this that I talked about, different slices, the first stars, first light, dark energy, dark matter, are observationally driven. Okay. So we have data to kind of support or refute the models. Now, the moment we go into other universes, like parallel universe, which is theoretically very much possible, we currently simply do not have any observations. So right now, the answer to your question really is universe is expanding into itself. And I know it's a very cryptic statement. It's like, you are on a balloon, which is expanding. And I don't, or no one can tell whether there are other universes that it is expanding into, unless we have some kind of testable prediction, which we don't have right now. But yeah, theoretically possible, observationally difficult to verify.
So do you think that in a specific or like volume of a space, if I put like in an infinite energy, then would that infinite energy does not make some changes in the flow of time? Like in the initial universe, there was like an infinite energy in a very specific, in a very limited space. So that a infinite kind of energy would not make a change in the flow of time.
Yeah. So again, this ties up, or in spirit, this is similar to the question, which is, do we have, for example, could we have metal production before the first stars, right? So all of these questions that, okay, there might be this extra injection of energy at very high redshifts. The question is that, can it be tested? Okay. Or in some way, what we call as falsifiability. That if I have an hypothesis that, okay, there was some time in the early universe when there was a very high injection of energy of some sorts at a certain location. The question is, how do I test with the current observation? So for example, would it have an impact on the CMB anisotropies? Would it have an impact on the way galaxies are being separated right now due to acceleration? So right now, with all the observations that we have, including CMB, we do not have any information or support for these ideas. Okay. So then what we have to do is, whenever we have these kinds of hypotheses, we have to form a prediction that, okay, if I go, for example, look at polarization of CMB, temperature anisotropies, or something like that. And if I see that, or rather if I don't see that, I know that my theory is wrong. That kind of thing has not yet come for any of this. There are people who work on energy injections in the early universe, but they have not been tested or in some way verified.
Sir, a question regarding the 20 centimeter observation. Sir, I think you guys are plotting the H8 map, right?
Sorry, you're plotting?
Plotting the H8 intensity maps, right?
True. Yeah, H1 intensity maps, yes.
So with plotting them, how can we interpret about the first task? I want to know about it.
Yeah,
So,
no, that's a good question. The reverse engineering problem. So see, in simulations, what we do, you have these stars, right? And they are forming in these galaxies. The galaxies are emitting radiation. And what you are studying with the 21 centimeter intensity mapping is the brightness of the 21 centimeter line, right? And that, in some way, you are reversing that problem to then understand about stars and galaxies. So what you measure really is how bright the 21 centimeter line is as a function of redshift, right? From redshift 6 to 30, or in this plot from 100 million years to roughly 1 billion years. So you take the slice, for every vertical line, you have one number, then this is the intensity of the 21 centimeter line. So then the question is, once you have this line, you can reverse engineer and say, okay, this line behavior could only be explained if stars and galaxies had these properties. So it's not a direct measurement, it is an interpretation.
so the data we have on now, we compare it with them. So we data we have on the galaxies now, we compare it with them.
Okay. Yeah. But maybe I should have clarified. This signal has never been detected by anybody, including us. Okay. So we have never seen radiation from this side in 21 centimeter at all. So, and this is mostly because what someone mentioned, the telescopic contamination, what we call as miscalibration, is what is stopping us. But yes, once we have a detection of the signal, and there is not one signal, but many, I browsed over it, but essentially you're looking at brightness of the line as a function of frequency. Each frequency corresponds to a redshift. So we don't know what the signal really looks like. But the point is, once we have that signal, you can reverse engineer and reconstruct masses, luminosities, all of that.
Thank you.
Well,
one more question here.
Sir, it's completely out of topic, but since when we were discussing about that there are certain possibilities that universe existed before the Big Bang too. And since string theory is one of that thing that can be of contradicting to what we're discussing right now, what would you comment on the basis of string theory?
Yeah. So basically, we are alluding to the inflation or pre-inflation era, right? Where our current physics cannot explain things right here, because you need GR, the general relativity, and you also need quantum mechanics. String theory was an alternative to be able to unify them and explain this. But unfortunately, I should say, it has not been able to do so yet. What is more important here, again, I'm back to the data. So if if the string theory is correct, yeah. So then from here, if string theory, for example, is correct, which we do not know, the question is again, if we are able to unify these things using string theory here, what prediction does it have so that we can verify that it is the correct version, right? So again, the falsifiability. That is, if I have a theory, I need to come up with a prediction which can be tested. And this is where I personally feel that string theory lacks, which is it doesn't have a robust prediction which is unique to string theory. So for example, if it said, okay, if this is what happened, then on CMP anisotropy, you will see this particular power feature in when I go to the power spectrum. And we don't have that. So it is very hard to comment whether string theory can do anything here. But if it can, it needs to come up with a prediction that we can test with the data.
So maybe other general questions or any other topics that we wanted to ask Saurabh about.
I have only questions. So it is about the bandwidth of the spectrums. Hello, sir.
Saurabh, is it okay to go for one more question? Do you have we can also take it offline if you think, but there's one spectrum bandwidth question.
No, go ahead.
The question is like we have a discrete, like in atoms, we have discrete energies. Like the states are like electrons are not present in everywhere. Like we had noted there are orbitals in discrete energy. So if there are like different states where electron can be found, let's say why do we have a continuous band of a spectrum? It should be continuous. Right? Also, it should be a discrete. Like when we see the spectrum of visible light, then we see that they are ranging from violet to red. But there are energies in an atom. Electron are like mostly the probability of finding the electrons are mostly in orbitals, not anywhere. So when they are jumping from one state to another state, so there is a discrete energy. There should we have a like discrete energy band, not a continuous band. Then why do we have a continuous energy band?
When you say continuous energy band, do you mean this kind of a Planck spectrum, or do you mean recombination means?
So like we when we split electromagnetic spectrum.
Electromagnetic. So, there are discrete spectra also. So, Mayuri probably will talk about tomorrow about recombination line, which happened during the first atoms form. So, you have these electrons that trickle down to in their energy state and come all the way to the ground state. So, that spectrum, when you see, it will not be continuous. It will be having ripples. And the ripples actually will correspond to exactly what you said, the discrete lines. Okay. But that is only one way to produce radiation, which is transitional lines or rotational lines. But then majority of the radiation that we see, for example, from our galaxy, it is not coming because there are electrons trickling down the energy states. That can also come from other sources. Okay. So some of the sources that I counted, synchrotron radiation. So when a free electron, for example, is captured in a magnetic field and it rotates around it, that also radiates. And that radiation is not discrete, it is continuous. Similarly, if electron, for example, comes near a proton, right, and it kind of bends over like this, that also any acceleration of electron will produce radiation. And some of these radiation, I should say most of these radiations are actually broadband and not discrete. What you are talking about is one particular kind of radiation, which is this recombination radiation. And that, even in cosmology and astronomy, will be discrete. So you have to ask, whenever you see a spectrum, you should ask, what is the radiative process that resulted in this spectrum? So like this is black body, what I'm showing. There could be synchrotron, there could be the transition lines, right? There are different processes.
So one last thing. How is life at the Arctic?
So Girish will tell you a lot about life at the Arctic from his perspective on Saturday. I can speak for myself, it has been great. It feels like I've been here for 6 months, though it has just been 3 weeks. And he will probably show you a lot of pictures around. We are slowly transiting into daylight. I can see daylight, which is good, which was not the case when we came here. It's of course cold. temperatures are between -15, -20. With wind chill, they can go to -30. But it's a unique experience, and I think it's a lot of fun. But I will not spoil the game, and you will see a lot of these things along with some videos on Saturday.
Saurabh, I think we are going to thank you at this point. Thank you very much.
Sure. See you.